In a previous lesson, we saw how optimization is both a key piece of other analytics models we've seen in this course, and also a powerful tool in its own right for answering prescriptive analytics questions. Given what we know and what we can predict, what are the best actions to take? We also saw that in contrast to many of the other models we've seen where there's good software both to create a model and to solve it, in optimization we only currently have good software for solving models. Building optimization models requires a lot of human insight and expertise. So the next few lessons will help you learn the basics of optimization modeling. In this lesson specifically, we're going to see three key pieces of optimization models. Optimization models have three main components: variables, constraints, and objective function. Let's start with variables. The variables in a model are decisions that the optimization solver will pick the best value for. For example, if we're optimizing a political candidate's travels around the country, then we might have variables like these. Xi might be the total amount of time the candidate spends in state I, Yi might be the number of visits the candidate makes to state I, and Zi might be 1 if the candidates ever visit state I and 0 otherwise. We might also want to make more specific decisions, like which days the candidate visits each state. So we might have a variable like WID, the time the candidate spends in state I on day D specifically, and VID might be 1 if the candidate visits state I on day D, and 0 if not. These are all decisions that we're trying to make, and if we build our model correctly, the optimization software will then find the best solution, the best combination of values for the variables. The constraints in a model are restrictions on those decisions that we make, restrictions on values of the variables. For example, we might have restrictions like these. There are only 30 days left in the campaign, so the total time the candidate spends in all states can't be more than 30 total days. In other words, the sum over all states I of Xi, the time the candidate spends in state I, must be less than or equal to 30. We might also want to make sure, for example, that the candidate visits Florida at least 3 times in the last week, days 24 through 30. In other words, the sum over days D equals 24 through 30 of V Florida D must be greater than or equal to 3. And we need to link our variables together correctly. VID is the number of visits to state I on day D, and YI is the total number of visits to state I, so we need to make sure that when we sum up VID over all days D, the total equals YI. That's an important constraint. We might expect it to be true because of how we've defined the variables in English, but optimization solvers only look at the math. They don't look at the words of what we want the variables to mean. So if we don't use constraints to explicitly tell the solver how variables should be related, the solver will go happily ahead and find a mathematical solution telling our candidate to visit state I 12 times, but that each VID should be 0. The last piece of an optimization model is called the objective function. It's a measure of the quality of a solution, the quality of a set of values for the variables, which we're trying to maximize or minimize. In our campaign example, the objective function might measure how many additional votes we could expect the candidate to get based on the campaign schedule. Perhaps alpha times the population of state I times the square root of the time spent in state I plus a third times however long is spent in neighboring states, plus beta times the number of times each state is visited each day times a factor for the day. Maybe visiting too early or too late dilutes the effect. You might wonder, of course, how we know the values of alpha and beta and the square root relationship to the amount of time spent in a state and its neighbors. That's one of the ways that optimization can sit on top of other analytics models. In order to use the optimization model, we first need to use statistical methods like regression to find the right values of alpha and beta, to determine the relationship between time and votes, etc. In fact, it's pretty common for optimization models to require input that's found as the output from other models, and we'll see some examples when we get to the part of the course when we start putting a variety of models together to create a comprehensive solution to a question or problem. I've been using the word solution pretty loosely, but in optimization, a solution is a value for each variable. For example, the amount of time spent in each state. A solution that satisfies all of the model's constraints is called a feasible solution, and the feasible solution that has the best objective function value is called the optimal solution. That language is just like in everyday life. Feasible means it's possible to do, and optimal means best. Which brings me to one of my pet peeves. When you're talking about solutions to an optimization problem, please don't use the phrases more optimal or most optimal. It's like saying more best or most best, and neither one makes sense. So those are the three main pieces of optimization models: variables, constraints, and objective function, and the output of an optimization model, an optimal solution. But specifying the model itself is as much an art as a science. Sometimes the best answer is pretty straightforward, and other times the straightforward answer doesn't work. We'll see some examples in an upcoming lesson.